practice exam. And, the practice exam is an exam from a previous semester. It's not all inclusive, right? There might be stuff on the practice exam that doesn't show up on the actual exam. There might be stuff that's not on the practice exam that shows up on the practice exam. And I'll try to think about things as we go through here, but it provides you, kind of a level of difficulty and a format that you're going to see. It's all going to be multiple choice here. And even the very first problem here where maybe we would ask you to draw a picture, you're actually asked to just pick the FBD that would allow you to determine the weight of the block E if the sag S is equal to 3 feet. So here's our S over here, equal to 3 feet there. And we tell you to neglect the size of the pulleys. And I don't show all the choices here because I'm just going to focus on drawing the FBD and the process for going through and drawing that FBD. So what do we want in FBD? We want an FBD to have known values and not too many unknowns. Now we do know D is 5 pounds and we know F over here is 5 pounds. So those are known values and they go over these pulleys. Well, I don't necessarily need an FBD at this pulley right here because I know if the tension in this segment is 5 pounds, then if this is a frictionless pulley, and they will all be frictionless pulleys for now, then this is also equal to 5 pounds. So actually, this is really my known is that one, and then this one over here is equal to 5 pounds, and I'm looking for the weight of block E. And so I want to include what I'm trying to find, and I want to include some knowns there. Okay, so then I would go and I would say, okay, well, let me include what I'm trying to find. Let me cut through this, cut through that. And so now we're looking at an FBD that's going to have, basically, it's an FBD at A, isn't it? So we'd have 5 pounds there. We'd have a 5 pounds here. Actually, let me draw the FBD over here off to the side here, right? So we'd have a 5 pounds. Correct FBDs in statics are such that they have all the known values shown with their value on there. That 5 pounds at 5 pounds, we have a W here at E, and also includes all the geometry as well. So, right, this is a, this right here, that would be a 3, 4, 5. Include this geometry over here, the 3, it's not an angle, it's again, a 3, 4, 5 right there. But all the geometry on there. Now, if you're going through those choices, you won't see anything like the same thing with the geometry and without the geometry on this practice exam here. So, but right, we're going through this at this high level of just like, right, what are the overall processes and how do we approach these problems? So let's see. I saw some questions in the chat here. Multiple choice, yes, 100% multiple choice for exam 1. There may be some free response later on this semester. The study guide, there is kind of a study guide on Canvas. If you go to the very top, it's not like, oh, here's what to study necessarily, but it's more of a how to study. If you go to the top of my lecture recordings, here's a study guide approach, links to the study guide document, okay? And this is something not just for statics, that's also for any class. It's more of an approach. The practice exam is really the thing. I would look at the practice exam for sure, but also look at the study guide for other things that I suggest studying. And then, so would that include the 3, 4, 5 triangle? Yes. And then how do I figure out the 3, 4, 5? Never mind. Okay. Okay. Excellent. Okay, so I will be going through pretty quickly here the practice exam, but certainly let me know if you have questions. And like I said before, the solutions of practice exam are up on Canvas. Okay, and then actually this is not number 1, this is actually number 2. If they tell us, again, it's the same information, if blocks D and F are 5 pounds each, determine the weight of block E if the sag S is equal to 3 feet. Neglect the size of the pulleys. So basically they're just saying, okay, well now can you solve this? You pick the right FBD, now let's solve this thing. And it looks like if we do sum of forces in the Y is equal to 0, then we're gonna have only one unknown. We can solve for WE in that case. And so, you know, when these equilibrium problems, particle equilibrium problems, it's really about, once we get that FBD, the equilibrium equations is just looking at each one and asking ourselves, okay, should we do sum of forces in the X or should we do sum of forces in the Y? It's really about identifying options. Very similar to how we picked our FBD. I didn't really go through all the options, but we could have said up here, well, I could do an FBD at D. We could do an FBD at B. We could do an FBD at A. We could do an FBD at C, or we could do an FBD at F. And then we could go through and look at those and say which ones have knowns and which ones have the things that I'm looking for in that case. Okay, moving on now to another particle equilibrium, but now with a spring. Oh, and I do want to mention, you'll see this on the practice exam and you'll see this on the actual exam, that there are problems that are pretty easy, right? Like that last one. That should be pretty easy, where we do expect 90% or higher of the students to get that problem. There's other problems on the exam where we expect a much lower than 90% to get that question right. So don't spend a lot of time on a problem when you have these really easy problems that you haven't solved yet, right? So just good test taking skills. You will see a range of difficulty, right? Not every problem, even though they're all worth 5 points, not every problem is really the same level of difficulty. For instance, this one is probably a little bit more difficult than the last one there. And so for this one, we have this unstretched length of the spring is 300 millimeters. And so if we look down here, the original length of the spring is 500 millimeters. And so they're telling us, well, it's 300 millimeters. They give us a spring stiffness of 800 newtons per meter. And we're asked to find the force in BC when the spring is held in the position shown. Now remember, springs, one of our main concepts with springs is that the springs do not change equilibrium. They can, if they change geometry, they change equilibrium, but we can still think about picking our FBD and setting up our equilibrium equations exactly the same, whether there's a spring there or not. So let's look at what they're asking us to find. They want us to find BC. Okay, so let's cut through it because that's what we're looking for. So we definitely want to expose that. Now, basically what that does is it kind of leaves us with one choice, right? Like an FBD at B includes the spring because we do have info about the spring. It includes what we're trying to find. And so we're still going to do, our first step is still going to be an FBD at point B. And so we're going to have a tension in B to C. We'll have a tension over here in B to D. And we have this tension from A to B, or we could call it the TS for spring in there. Now we look at that FBD, and we do have our geometry. It looks like, there's a 4. We look at we can add our geometry to this because they give us all that stuff there. So we could certainly add that geometry, those slopes or angles, however we want to do that. But we look at this and we have 3 unknowns right now. And with 3 unknowns, well, our 2 equations aren't going to do anything. So we need to think about, okay, how can we incorporate this stuff with the spring? Well, Hooke's law says that F is equal to K times S. And let's see, we know K. And actually, if we look at what the info they gave us, they really give us S because they give us the stretch length and the unstretched length. And so S would be equal to 500 minus 300, or 200 millimeters. Now, be careful on this one that we are in millimeters here, but our K is in newtons per meter. So watch out there. That would throw you off by a factor there. But I think you would still get the correct answer. You would just have you would just have a factor of 10 or of 100 in there. So I see a couple questions here for the multiple choice. Is it for the turn-in part? Does that gain any partial credit? No, we rarely use that for partial credit. Maybe in like some weird circumstances or something like that. But it's really just so you have a record. Like after you go back and we release the results for the exam, you're going to look back and you're going to say, oh, why did I miss this question? And if you have some work written down, then you can look at that and say, oh, that's why I missed this question. And we'll post a solution and all that stuff. but having your work written down will benefit you from that. And then why did we subtract? We subtracted because in the position shown, right, the spring is unstretched in 300 millimeters. When the spring is in the position shown, right, the spring is at 500 millimeters right now in that position. We're trying to figure out what the forces are when it's in that position. If the spring was unstretched, then it would be point B would be, well, this is point B. It really wouldn't, we can't think about it that way, but basically it's saying it's only 300 millimeters long when the spring is unstretched, and so it wouldn't be attached to B, but then we stretched it out, we attached it to point B right here, and it gets to 500 millimeters long. And so then we can find, we have our S here, and then we can find the force in the spring would be equal to that 200, or we can convert it into 0.2 times 800 newtons per meter. Now we have and I guess this would really be the same thing we called over here TS, right? So that would be our 0.2 times 800. Now we have two unknowns. And so now we can sum forces. We can look at, okay, well, should we do some forces in the X? Should we do some forces in the Y? But we know those are our two options. In this case, I think if we sum forces in the X, we'd have two unknowns. If we sum forces in the Y, we'd also have two unknowns. So it looks like we're going to need both of those in order to solve our problem. Okay, and then did we figure this out, Sean? Which letter is that? It's a BC and a BD on there. Is my screen, let me know if my screen is blurry or anything. Okay, awesome. Okay, the problem numbers on my slides here may not be totally accurate. They may be off by one, or it may be okay. I can't remember. Yes.
I had a quick question on that last problem. When I solved it, I got 96 newtons. And I did it a few times to check and see if I don't know if anyone else had that similar.
Take a look at the practice exam, Luke.
Okay.
I'm pretty sure all those answers are, well, one of those answers are correct on there. Maybe, did you notice that these?
Yeah, I got it. I chose 97, and I think that's the right answer. But
okay, no, take a look.
1 Newton less.
Okay, yeah, that's weird. No, you should get closer than that.
Okay.
On these, so yeah, take a look at the practice exam solutions and see if you can figure out what went wrong, or office hours today too. Okay. All right, now 3D. In 3D here, we are asked to determine the tension developed in AD for the 900 Newton force applied at point A. 3D, you know, again, for picking our FBD, though, we want to have known values, and we want to pick, we also want to expose what we're trying to find, so we want to find AD. And so really, you know, our only choice in 3D, it's usually pretty obvious. It's where everything joins together. And so we would do an FBD at point A. Now, the only main difference between 2D and 3D that we've seen in our problems is that it's just nice to write out all of our force vectors. So let's write out the force vector from A to D in terms of the magnitude and the direction that we know. For example, this is a 3, 4, 5. AD is a 3, 4, 5 in the YZ plane. And so that's going to have a 0 in the I. It'll have a minus 3/5 FAD magnitude in the J, and then a positive 4/5 FAD magnitude, the magnitude of AD in the K direction. So even though like AD has an X, a Y, and a Z, or could have an X, a Y, and a Z, if we write out the vectors for each of those, FAC here, we do the same thing. We write out the I, the J, and the K. And then if we did FAB and the vector, and we wrote out the I, the J, and the K, what that does by writing out all those vectors, and then let's also include the weight there, or the force applied, whatever that 900 newtons is going down, that would be a 0I, a 0J, and a minus 900 K hat. And it's minus 900 because it's going in the negative Z direction. So if we do that, what that gives us is all the info that we need for equilibrium. Because then we say, well, which equilibrium equations do I need? Do I need sum of force in the X? Do I need sum of force in the Y? Do I need sum of forces in the Z direction? And so we can handle 3 unknowns when we're in 3D. And it's even more important that we can pick which one we're going to use first, second, and third. So I haven't written out all my vectors, but if we had all the vectors written out, we could look and say, oh, if we want to do sum of forces in the X, we just need to look at all the I components. If we want to do sum of forces in the Y, we just need to look at all the J components. And so we could look, and like sum of forces in the X, we might see, oh, there's 2 unknowns in that. And sum of forces in the Y, there's 2 unknowns in that. And sum of forces in the Z, oh, there's only 1 unknown. And actually, it's what I need. So this is, sum of force in the Z is the only equation that we need in order to solve that problem there. So our steps for 3D particle equilibrium were to say, okay, well, here's all my force vectors. And then once we have all the force vectors, then we can go into our equilibrium equations. Very similar process for this one. And what we want to do is we want to be developing these processes that can be implemented in any problem. And if you look at my study guide approach, which is in my lecture recordings page where I post all my lecture recordings, it's going to talk about how to develop that process and kind of how to refine your techniques. It's not like a solve all or like a fix all or anything like that, but it's something that you can use to adapt to your needs over the years and become a more efficient student. So for example, let's talk about that same process for this one. Right, we talked about, okay, well, first, given the weight of the bucket is 750 newtons and the unit vectors are given, select the correct equation for sum of forces in the X direction. Well, this is just part of that process because we would do an FBD at A because we know this is 750 newtons going down. They give us, instead of having to do all this geometry stuff here, they give us the unit vectors and they say, okay, we're just summing forces in the X. Well, isn't summing forces in the X just going to be grabbing all of those I components there? And so we say, okay, which one is a 0.6 for AB, a 0 for AC, and then a 0.58 negative for AD. So we can go, okay, well, this one could be there's a 0.6. That one doesn't work for AB. That one doesn't work, or this one and this one could work. Okay, we need a 0 for AC. Oh, there's a 0 for AC. That's not a 0, right? And so we're basically just looking for, right? That's part of our process there. And so having a process that you can use for this problem that also works for the previous problem we were working on can be very beneficial for us in statics. Also, another thing about the statics exam is, and I think you will notice this with the practice exam, I don't know if any of you all timed yourself, like sat down and just said, okay, I'm going to take the practice exam, see how long it takes. That 90 minutes goes by fast, right? You don't have a lot of time to look stuff up. So I would recommend having everything written down. Like if you're like particle equilibrium, be like, okay, here's my main equations, here's my process, and things like that. And then also remember, like I mentioned before, don't spend a lot of time on a problem that's really hard when you haven't gotten to those easy questions yet. Okay, now on to moments now. We're asked to determine the magnitude of the moment about point B for this 800 Newton force shown. And so what's our process for moments? If we're trying to find a moment about point B, well, we need to we know the equation is m is equal to F times D in general, right? Where D is that perpendicular distance. Well, if we see something that is at an angle, I am going to look at this 160 millimeters, the 200 millimeters, and say, okay, well, I know some distances that are horizontal and vertical. So let's break this up into horizontal and vertical. And so we take, oh, this would be 800 times the cosine of 60, and this would be 800 times the sine of 60. And then I just need to figure out, in terms of my right-hand rule, which one are negative and which one are positive for those lines of action. Do you have a question? Somebody have a question? Kolov, you have a question?
Yeah, no worries.
Kolov's taking a phone call during class. Okay. So we have 800 cosine 60, 800 sine of 60 right there. And then remember, these lines of action extend infinitely in both directions. And so we can think about these forces being applied anywhere along those lines of action, and then whether they cause negative or positive. I think the horizontal component, that 800 cosine of 60, that's going to cause a rotation that way about point B, which would be negative. And the distance would be that 160 millimeters. The 800 sine of 60 is going to cause a rotation also in that direction, which is negative. Remember, in 2D, positive is always counterclockwise. And so both of those would be negative. And then how far away is this vertical one here? How far away is that vertical component from B? It's that 200 millimeters. And so then we can plug that in and solve our problem there. So that was our general process for kind of an easier problem. Now how about this one where we have some more geometry stuff going on, and they're asking us, again, same thing, find the magnitude of the moment about point D. And so they want us to find the magnitude of the moment right there. The tension in the cable is 1 Newton, and the distance is 1.315 right there. And this forms an angle of 30 degrees. And so we think about, okay, well, we know our line of action is here. And remember, because of the principle of transmissibility, we can use any point on the line of action. Now, in terms of our location relative to D, where do we know on the line of action? We know point E. We know where that is on the line of action, right? It's 1.315 plus, or yeah, 1.315 from D horizontally, or we know this point on the line of action. So we could use either one of those points for our 1 Newton that's applied to this. And actually, it doesn't even matter what direction you put the 1 Newton. And we knew that when we wrote this question, you know, put it in either direction here. It wasn't my favorite because of that. And so we try to avoid that kind of thing, you know, just, you know, to make it perfectly clear, especially in these remote online exams here. I'm going to draw my 1 Newton going down and to the left, and I'm going to do it at point C. Well, even though there's like this new stuff going on here, I'm still going to follow the same process. I've got a force at an angle, and I know horizontal and vertical distances. So let me break this up into horizontal and vertical components. I think if I know this is 30 degrees and this is 1 Newton, I think I can find that horizontal component and I can find the vertical component. And now all I have to do is say, okay, well, what moment is this causing? And actually this point, that point, I kind of got sloppy here with my writing, but this 0.2 meters right here is telling me where point C is. So really the Y component of the force should be more right here like that. And so I know I'm 0.2 meters away, and I can figure out negative and positive based on that. And then this horizontal component is 0.875 away. So with that process, we can take a problem that looks totally different than anything we've seen before, and don't think that oh my gosh, my process is going to be different now, right? No, it's going to be the same process. So come up with that process that can work for any problem, and then stick to it. Even though you might question yourself and say, oh my gosh, is that the same process? Yes, it's going to be the same process. You can do the same things. It's very much true in 3D as well for moment vectors. We're asked to find the moment vector about point A. You know, if we're given FBC and the corresponding vector, notice that a lot of these problems, we give you a lot of information, right? We're not like asking you to solve them all the way from scratch. We do know that the the exam is is only 90 minutes long, and we try to write it for certainly a 90-minute exam. We usually have, if you look at previous averages, our averages are typically in the 70s, somewhere from the low to the high, depending on the semester. It just kind of varies. And I've never seen an exam where we don't have at least like 10 students getting 100%. Okay, so they're very feasible exams, right? It's not like we're trying to make these impossible. But I just want to prepare you all, right? I want everybody to do as good as they can. And so that's why I'm saying these things. Okay, so if we want to find the moment about point A, this should be our process. We know is going to be an R cross F. And we just have to figure out what R do I use and what F do I use? Well, F is given, right? We already know that. R, remember, we can go to any point on the line of action of the force. So we could do R from A to C, or we could do R from A to B. Either one of those R's will give us exactly the same answer. And then see a couple questions in the chat here. Are the tests going to be graded right after we submit it? No, I'm not going to. We're not going to post grades until everyone has taken the exam and the makeup exam. The other thing too is I always like to check through everything, make sure there's no problems. If there's a problem where only like 20% of the students got it right or something like that, myself and the other instructors will look and say, oh, you know what, should we throw this question out or something like that? And I don't want to release the grades and then be like, and then change your grades. So it will not be available right away. And then I see RDC cross F, RDC. Yeah, and then I think Kala, you were talking about this problem, right? You absolutely could. And actually that's in 2D, you can use R cross F as well. Okay, yeah, and it would be R from D to C cross F in this one, or you could do R from D to E cross F. So same idea in 2D as in 3D, that you can use any point on the line of action. And yeah, don't be afraid in 2D to use that R cross F stuff. For sure. It'll do all the signs for you. It'll do all the perpendicular distances for you if you figure out your your R vector and your force vector. Okay. Number 9 now. Moment about the CD axis caused by the tension in AB. Which position vector will not work for the position vector R in the triple scalar product? So our triple scalar product is R cross F dotted with the unit vector. And so this is testing part of that, right? This is just testing a piece there. Well, remember, we can go, when we're doing this, this can go from any point on the axis to any point on the line of action. So the axis is C to D. So we can go from any point on C to D to any point on the line of action. So that would be those two, or we could do from there to there and there to there. So any one of those position vectors is going to work. F, there's usually one F, and then the unit vector is always on the axis, and so we could use the unit vector from C to D, or we could use the unit vector from D to C. It doesn't matter which direction the unit vector goes. Okay, now we're actually asked to solve that same problem. So now we're given F, all the components of the vector. What is the magnitude of the moment there? Now let's say we picked point C, R from C to A, cross the force there, A to B, and then we dotted it. Let's say we dotted it with the unit vector from C to D. Okay, and I'm not going to go through all the math. You can take a look at the practice exam to go through that math. This is the most important part, right? If we can set up the r cross f dot with the unit vector, pick all those vectors, we're good to go. We should, right, that math should be good. Now, let's say out of this, I get a negative number. I don't know what the answer is. I can't remember what the answer is. Let's just say I get a negative, I can't remember what the answer is. I don't know. Let's just say I get a negative number, okay, out of this. What does that negative tell me? When we're doing the dot product, even though we get a scalar out of this, we also get sign out of that. And so we might get a negative number. We might get a positive number. Let's say we get a negative number. And that negative number tells us that it goes opposite the actual vector. So it tells us that the moment goes opposite the unit vector that we picked from C to D. And so if that's the case, if we do get a negative number, and we will get a negative number the way we set this up here, then that means that our actual moment vector along C to D is actually going from D to C, not from C to D. So we picked C to D in our unit vector, but we got a negative number. That means it goes opposite, and so our moment vector is directed from D to C, not from C to D. If you picked the unit vector from D to C, you would end up getting a positive moment. And then you would say, oh, well, it goes in the same direction as D to C, and so we get the same answer, D to C. You could use the right-hand rule for this to say, okay, my force vector is here. I do think we're going to get rotation going in this direction. And then if I take my right hand and curl it in that same direction as my tendency to rotate, my curving arrow, my thumb is going to point from D towards C as well. So you can think about it in terms of what direction the tendency to rotate is too. Okay, number 12 here. If the magnitude of F is 100 pounds, determine the resultant couple moment. Now that we're in couple moments, and we have two sets of equal and opposite forces in this one, right? We've got a minus F and a positive F. We've got a 200 pounds going to the right, a 200 pounds going to the left. This one, when we have equal and opposite forces, we know the moment about any point is the same. If you look back at our lecture notes, the first example we did was we took the moment about different points and we got exactly the same answer every single time. And so what we did with that is we said, well, let's pick points that make it easy. So for the 200 pounds, I'm going to pick a point that's on the line of action of one of the two of those 200 pounds. So I'll pick the moment about this point. So I'll take the moment here for only the 200 pounds. And then I'll take the moment here or here, either one, doesn't matter, on the line of action of either one of those. I'll take the moment here for the 100 pound. And then I'll just do like we normally do with moments in 2D, where I'm just looking at if they cause a negative or positive rotation, and then multiplying them by the correct distance. And then, so all we have to do then is we'll just add this and add this, or subtract, whatever the case. We add them together, but accounting for negatives. And then so we would just add these two, add together, and that's our final answer. So there really is no difference if we have a couple moment, if we have, not a couple moment. So, if there's not equal and opposite forces, it doesn't really matter. It just means that we can be, they notice that they don't specify what point to take the moment at. And it's because it doesn't matter. We're going to get the same thing. And we just want to reduce the number of equations that we have to do. And so that's why we pick a point on the line of action of one of those two equal and opposite forces. Well, and we have to add the two because both of them are acting on the system. So when we take the moment for the 200-pound force about this point on the bottom left, that'll give us only the moment for the 200 pounds. I'm only using the 200 pounds. When I take the moment here, I'm only looking at the F's, the 100 pounds. And then I wouldn't worry about finding the distance between the two F's. Again, when we're taking moments and they're at an angle, I would break that up into X and Y components. So I'd break this up into X and a Y. I'd break this one up into an X and a Y. I wouldn't try to find that perpendicular distance. I would just break them into X and Y components. And then don't we know the perpendicular distances between the X and the Y components already? So we don't have to do any crazy geometry. Good question. Okay, on this one, this is asked to find the resultant couple moment for the 30 and 20 pound couples. They're in the Z direction and the X direction, respectively. Even now that we're in 3D, again, we have equal and opposite forces, right? We have 30 pounds and we have 30 pounds. We have a 20 pounds and a 20 pound. Again, I'm going to pick a point on the line of action to make my life easier. So maybe I would do, for the 20 pounds, maybe I do R from E to D crossed with a positive 20I. And then for the other ones, for the 30 pounds, maybe I do R from D to C. So R from D to C, and then I would cross that with a minus 30 K hat. And I'm figuring out my K hats and my I hat, negative and positive, just based on my picture here. This 30 pounds is going in the negative Z direction. That's at the end of my position vector. And so I use the minus 30. If I could have done the same thing. I go R from C to D crossed with a positive 30 K hat. So that, because that would mean my position vector ends at D. And what do I have at D? I have the positive 30 K hats, right? So either one works, right? We're going to use either position vector. And then again, I would add these two together. Whatever I get, I'm going to get an IJK and I'm going to get an IJK, and I would just add those two together. Okay, this one, we are asked to determine the resultant couple moment for the three couple moments shown. So we're given the pure moments, right? Like these are already, they don't give us forces, they just tell us the tendency to rotate. I believe we corrected this on your version of the exam, but there's a little dash line here, or there's something that tells you what plane these are in. And then also, I believe also we show some arrows on here as well. Like there's an arrow going this way on there, and that's telling you what direction that moment is going. This one, there's an arrow going this way. And then on this one over here, there's an arrow going that way, which is how you saw this on the homework. And so assume those purple arrows are already there, and we know where there's some indication of where that 20-degree angle is, like a vertical line that's parallel to the y-axis, and then that tells us that this is below the z-axis in the yz plane. Okay, so now basically the way we do this when we have just pure couple moments in 3D is the same way we would do force vectors. Like if this was a force vector, instead of 1200 Newton meters, if this was just 1200 newtons, wouldn't we just figure out what the components of this force were? We would say, oh, well, this has an x component of 0, right? This is a 0i, and then this is in the y direction. Oh, it's kind of pointing in the positive, that arrow is pointing in the positive y, so it would be a positive 1200 times the sine of 20, and then it's pointing in the positive z, so positive 1200 times the cosine of 20. And so we treat these exactly the same way we treat force vectors when we're trying to find the resultant force vector. We're just looking for the resultant couple moment. The only difference is the units, or newtons per meter, or Newton meters, and when we're dealing with forces, they're in newtons. And then the other difference is that in moments, this is the axis of rotation, right? These are arrows are pointing on the axis of rotation, while in a force, they're pointing on the line of action. Okay, but if we know that axis of rotation, we can find the IJK. We can set this one as IJK. We can set this one as IJK, and then we just add the components together, add I's, add the J's, and add the K's in there, and to find the right answer. Why is there a 0I? Well, this one right here at point B over here, that one does not have an X component. That one is in the YZ plane, so the X component is 0. Okay, now we're stepping back here to the beginning of the semester, where we have these parallelograms. This was actually a homework problem, and sometimes we do that. We'll grab a homework problem and throw it on there. So that the homework is definitely good to look at. Our process for these ones, if we have this F of 26 pounds, what is the component along line AA? Well, our process was to look at, if we go back to the beginning of the semester, to look at transferring information from the tail to the tip or from the tip to the tail. Right now in this one, everything is touching at the tip of this F. And so we have this line A, it's touching at the tip. Well, let's take that information and let's draw the line A back here at the tail of that force vector. And then for line B here, we have line B is touching at the tip of F. Let's draw a line parallel to that back here at this one. There's how we get our parallelogram. And so with that parallelogram then, we can now go into our corresponding angles and we can figure out, okay, well, this 80 degrees, that's from a black line to a blue line. Where else do I have a black line to a blue line? Oh, there's a black line to a blue line. So that's got to be 80 degrees right there. I've got my 60 degrees. That's from a black to a purple. Oh, there's a black to a purple right there. So that's got to be 60 degrees. And actually, we can get, this one has to be 40 degrees then, just from summing the interior angles on that triangle. And so then we go into our sines, law of sines, and law of cosines to solve this problem. Again, remember it's these processes, right? And if we can apply the process here, we can apply the process to other problems as well. We have some alpha, beta, gamma stuff. I feel like this one is, I'll let you all take a look at that one. Oh yeah, let's do the planar projection here. So we have this F2, and they ask us to figure out what's the x component of F2. Now, this planar projection, depending on how you look at it, I can't, like, is F2 like going below the y-axis? Is it kind of going towards the x-axis? Like, where is it going, right? Now remember, our process was to identify parallel lines. So isn't this line right here, that's parallel to the x. This line right here, that's parallel to the z. So now I know, okay, well, if I can find that side of this right triangle, that's going to be my z component. If I can find this side, that's going to be my x component right there. And then, oh, where's my y component? Well, my y component is actually touching the y-axis, isn't it? So if I could find that side, that would be my y component. Okay, now that we know what lines are parallel, can we kind of tell where this thing is sitting? If this line is parallel to the x-axis, doesn't that mean that this has to be a 90-degree angle right there? And then also that this point right here, that has to be, this line has to be in the XY plane, doesn't it? For that spot right there. And so that's telling us now where stuff is located. Okay, that's in the XY plane. That also means that this angle right here must be equal to 90 degrees. There's my 90-degree angle right there. Now we've identified our two right triangles, and we just have to break them down and say, okay, well, if I know this side right here. I know this is 500, and that's the hypotenuse of the 45. So I can find this side over here would be using the sine of 45. This side I could find using the cosine of 45. But I really want the x component, which is this side right here. And so with that one, I would need to take my fxy times the sine of that 30. So it would really be the whole thing, my fx is really going to be 500 times the cosine of 45 times the sine of 30. So, you know, look at these planar projections as those two right triangles, and you got to find those parallel sides. I know I'm out of time here. We didn't cover the last few here. I'll let you all take a look at those on your own. Remember, the solutions are up on Canvas there. And also, let me know if you have any questions. Send me an email. Stop by office hours this afternoon from 3 to 4:30. Good luck on the exam. You all have a great rest of your Wednesday. We'll see you tomorrow night. The magnitude of the projection in 19, I am not sure off the top of my head. Determine the magnitude of the projection of FAC onto line AO. So what we need to do for this problem, though, Eilish, is I need to come up with my force vector from A to C. And I would do that based on my position vector, knowing my coordinates of A, finding the coordinates of C. Oh, no, wait, they gave us a FAC. Never mind, we don't have to do that, right? They gave us FAC. So that we don't have to do that part, which is good. I was just thinking, wow, that's really long. And then we want to find the projection onto AO. Now, we will need the chords of A still and the chords of O. I want to find the unit vector from A to O, and then I just take FAC dotted with the unit vector from A to O, and that would give me my magnitude. So I don't know if that helps. I do have to run to my next class. If you have any questions about that, anyone send me an email or stop by office hours this afternoon, and we'll see you all later. Oh, what does that mean? Okay. Well, I don't see Eilish here anymore, but she can reach out, hopefully. All right, Brent, Kyler, you all good? Okay. Take care.